Hello. Today we're going to talk about a very important topic. It's magnetic flux and Faraday and Lenz's law. This is kind of the principle behind all kinds of cool stuff. Most importantly, it's the principle behind generators. So almost all electricity on Earth is generated using generators. There are some exceptions, but the vast majority of it is. Nuclear power, hydroelectric, gas, all this stuff is using generators. So let's talk about what that is. So first of all, we need to have the idea of magnetic flux. Magnetic flux is, the easiest way to think about it is, you know, these magnetic field lines with the magnetic field. Think of magnetic flux as how many field lines you got captured by a loop of wire. And keep in mind, you can have just one loop, or if you have a loop wrapped like 20 times, you get 20 times the flux. So anyway, let's talk about the flux with one loop though. Remember, the stronger the magnetic field line, the more dense the field lines. And you're going to capture a whole lot more if your loop is perpendicular to those field lines. Or if this is how you do it, you use the normal of the loop, same normal we have for normal force, or the normal we're measuring with law of reflection and law of refraction, Snell's law stuff. So yeah, if you've got your normal of your loop, so imaginary line coming straight out of the middle of your loop, parallel to your magnetic field, you are capturing as many magnetic field lines as you possibly can. We're going to use this cosine term to figure out the effectiveness of our orientation. If we do stick our loop in a magnetic field like this, notice we are catching 0 field lines with it. And at cos 90, we've got a 90 degrees between our normal and our magnetic field. So cos 90 is 0. Shockingly, we're not catching many field lines that way. And for something like this, we're catching some, not as many as we would if we oriented it like this, but some. The A cos 90, this part right here, I tend to think of it as we are solving for the perpendicular area. So kind of our effective perpendicular area to the magnetic field. Yeah, it's not a bad way to think about it. All right, again, we always measure our angle with the cos theta between the magnetic field and the normal to our loop. The normal line, imaginary line coming out of the center of the loop. And that'll get you your magnetic flux. Our area should be measured in meters squared because we use meters in physics, our SI units. And so if we take our magnetic field in Teslas, multiply it by our area in meters squared, we get Tesla meters squared, or we've got this new unit, Webers, which actually has an abbreviation. It's our first unit abbreviation with more, well, I guess, no, we've also done kilograms before, but no, never mind. The base unit is just G. So this is our first unit with more than one symbol. Webers is WB, and again, it's kind of how many field lines you're catching with this loop. Equivalent to Tesla meters squared, measured in Webers, and this is magnetic flux. You might be like, why do I care about catching magnetic field lines? It turns out that interesting things happen to a loop of wire if you change the flux in it. So there's a bunch of different ways we could change the flux. We could move the magnet away or towards the wire, so we could put it into or out of the magnetic field. We could change the area of our loop somehow. That would change our flux. If we made it bigger, we'd catch more field lines. If we made it smaller, we'd catch less. This whole rotating idea is a huge one, and that's the big one in generators. You rotate a coil in a magnetic field. Usually with many loops. Yeah, and make sure you're rotating the wire along an axis that's perpendicular to the field. If we just kind of like spun it around the central axis, the normal line in the center, it would not do anything. You would not change the area. But if you rotate it along an axis perpendicular to the magnetic field, you got tons of changing flux. So, just recapping that formula that we've been mentioning. Your magnetic flux is measured in Webers or Tesla meters squared, and to solve for that, you take your magnetic field in Teslas, or magnetic field strength in Teslas, multiply it by the area of the loop in meters squared, and then times cos of the angle between the normal of the loop, remember imaginary line coming straight out of the center, and the magnetic field. Now here's the interesting part. If you change your flux through a coil, it will fight the change. I tend to think of coils like people who like things like back in my day, we did it like this and I liked it. So I tend to imagine coils as being people like that, like back in my day, we did things right. They like things the way they used to be, but they got short memories, so they'll quickly get used to a situation, and then that's the ideal used to be that they want to come back to. So if you reduce the field in a coil, it will induce a voltage in the coil that will move current in such a way that it increases the field. So you take away some of its magnetic field, and it's like, back in my day we had a big magnetic field through us, and that's the way we liked it. And so it'll induce a voltage in itself that, in such a way, using the right-hand rule, that it will increase that field through the center for a short time. It'll eventually get used to it, and then no voltage. And if you increase the field in the magnetic field, it's like, back in my day, I used to like we didn't have very much magnetic field, and that was good. And so they'll induce a voltage that'll move current to decrease the field. It'll create a magnetic field in the opposite direction that cancels out part of the increase for a while. Again, you need constant change to keep a constant voltage. And if you change the direction in it, it'll create a voltage that'll move current to reverse the field. It'll create a field in the direction that it was originally. And these changes will always reduce the magnetic field for a bit, but they never eliminate entirely, and they're principles that determine how generators work. All right, so let's go over an example. Here is our big formula. Faraday came up with this brilliant law. He's like, all right, if we want to figure out how much voltage we're generating in a coil, we take the number of loops of our coil, this N is our number of loops, multiply it by our change in flux, so how much did our flux change, and divide it by our change in time. Keep in mind flux is BA cos theta, so you might need to do a BA cos theta up here if you don't know the change in Webers offhand, and usually this will be NBA cos theta. Anyway, so Faraday came up with this very useful rule for figuring out voltage, and then Lenz is like, hey, coils are like people who like things the way they used to be. So I'm going to tack this negative sign on it, and then I get my own law, and it's just going to imply that, hey, if you change the flux in a coil, it will induce a voltage that tries to undo that change a bit. All right, so here's another Faraday's law of induction, and Lenz's law with his negative sign. All right, that is it for today. Keep in mind that this guy will change a bit. I'll do a sample solutions from the upcoming homework, because that might be a little tricky at first. But yeah, super useful idea. You can make rail guns that fire loops using this. It's responsible for generating all the electricity around here. Yeah, very, very useful thing to know. Faraday's law of induction and Lenz's law. Thanks for listening. Bye.